We will now develop the concept of electric potential from the electric potential energy in exactly the same way we did when we developed the concept of the electric field from the electric force. Namely, when we saw the Coulomb force on a charged particle at a point in space was proportional to its charge, we defined the electric field, a property of the space, as the force per unit charge. We will now do exactly the same thing with the electric potential energy. Since the change in the particle's potential energy is proportional to its charge, we will define the electric potential difference, a property of the space, as the change in electric potential energy per unit charge. We start from the definition of the electric potential energy in terms of the work done by the Coulomb force. Now, the work done by the Coulomb force F as a charged particle is moved from point A to B is equal to the integral of F dot dl from A to B. We can express the Coulomb force at any point along the path as the product of the charge and the electric field at that point. From this expression for the work done by the field, we can obtain the expression for delta U, the change in electric potential energy of the charge as it is moved from A to B. And then note that the change in potential energy is proportional to the charge Q. Therefore, we can divide delta U by Q to obtain our final expression for delta V, the electric potential difference between A and B directly in terms of the integral of E dot dl along any path connecting A and B. For example, to determine the electric potential difference between A and B due to the electric field produced by a point charge at the origin, we need to integrate kq over r squared. The result is that the electric potential difference is proportional to the difference of the inverse distances of A and B from the point charge. This potential difference, delta V, is the physically relevant quantity. But note that it is defined in terms of 2 points in space, A and B. It is common to introduce a quantity V, which is defined for each single point in space, as the difference in electric potential between that point and some reference point, R0, called the zero of potential, i.e., V of R is defined to be equal to the potential difference between R0 and R. For our example of the electric potential produced by a point charge at the origin, it is common to choose the zero of potential to be at R0 equal to infinity, so that V of R simply becomes equal to kq over R. The dimensions of potential, or potential difference, are joules per coulomb. The common unit for electric potential is the volt, defined as 1 joule per coulomb. I'm sure you're familiar with batteries, devices whose purpose it is to provide a constant potential difference between their terminals, as measured in volts.